In this video, we're going to cover all of the examples that go along with section 8.6, which has to do with molecular shapes, which in other words means molecular geometry. So before we start, you either want to have your molecular geometry chart handout handy. Otherwise, you can of course flip back to the chart we filled out in the notes. But either way, make sure you're looking at something where you have all of the molecular geometries listed. So whenever we try to decide what the molecular geometry is, which is what it's asking for here, predict the molecular geometry, your first step is always going to be to draw the Lewis structure. Even though it doesn't explicitly say it, that's always our first step. So we're going to need to draw the Lewis structure, and then to get your AXE notation, because once we get their AXE notation, that's what's going to lead us to our molecular geometry. Now, I'm also going to add one more thing to this question because your textbook likes to also ask what the electron pair geometry is. So we're going to say, and the electron pair geometry, which remember, the electron pair geometry is essentially the starting shape, and then your molecular geometry is the actual shape the atoms make, ignoring the lone pairs on the central atom, essentially. Okay, so for both of these, pause the video right now and draw Lewis structures for HOCl and SiO4-4. So pause the video and just draw your Lewis structures. Okay, so if you draw your Lewis structures correctly, this should be what you have. Over here we have this one, and over here we have this one. So now that we have our Lewis structures, our next step is to determine the AXE notation. So remember that X's are atoms attached to the center, and E's are lone pairs of electrons on the center. So if I look at this one, I have 1, 2 attached atoms, and 1, 2 lone pairs of electrons on the center. So we would say that this has a AXE notation of, hold on one second, there we go, AX2E2. Looking at the other one, I see 1, 2, 3, 4 atoms attached to the center and no lone pairs on the center. So we would say for that one that this one would be AX4. Okay? Now remember that AXE notation doesn't actually mean anything. It's just a way to help us get our electron pair and molecular geometry. So our electron pair geometry is based on the fact that we have 2 plus 2, so 4 total attachments. So if you have 4 total attachments, if you look that up on your chart, you would see that that is a tetrahedral to start with. But our molecular geometry, once we account for the fact that it's 2 X's and 2 E's, you would see that AX2E2 corresponds to a bent geometry with a bond angle of 104.5. So there we go. Now, if we look at our Lewis structure here, notice this is not very bent. This looks pretty linear the way I have it drawn. You do not have to draw it in 3D, but if you would like to, just to get a better idea for what that would look like, in 3D it would look more like this. So there's that, our electrons are on the top, and then that bound angle there is the 104.5. Okay? Now, if we look at our other one, looking at this one again, AX4 would correspond to 4 total attachments. 4 total attachments means our electron pair geometry is a tetrahedral. But what we also see is that if they're all atoms, our molecular geometry is also a tetrahedral. So in this case, the electron pair and molecular geometry are the same. Okay, all of our bond angles in a tetrahedral are 109.5. Again, you do not have to draw it in 3D, but if you look on your chart, you'll see it represented there. Essentially, these 3 atoms are in the same plane, and then one oxygen is coming out towards you as the base of the pyramid, and the other one is going back into the page as well. So essentially, it's kind of a base of 3 pyramid with one sticking out of the top. Okay, so that would be what it would look like in 3D. Okay, moving on to our next example. Example 8.7, take the same approach. Pause the video right now and draw a Lewis structure for HCN. We will then also decide the electron pair and molecular geometry. Okay, so if we look at our Lewis structure, hopefully you had this. So now that we have our Lewis structure, if we do our AXE notation, I have 1, 2 atoms attached to the center. Remember, we don't care that these are triple bonds. We're just counting the atoms attached. So there's 1, 2. There are no lone pairs on the central atom, which makes this AX2. Okay, so an AX2 notation means that our molecular geometry is linear, but 2 total attachments means that this is also our electron pair geometry of linear. Okay, either way, our bond angles would be 180 degrees. So to make this 3D, it's very simple. All you really do is just draw the angle in there. Okay, so there's 8, 7. Now, if we look at 8, 8, there are a bunch of molecules here in 8, 8. So I'm going to go through these a little bit quicker. But again, pause the video right now, draw Lewis structures for all 6 of these different molecules, and then try to figure out the AXE notation and geometry prior to going over the answer. So pause the video, draw your Lewis structures. All right, so take a moment and check your Lewis structures. They should look like this. Then you want to go back and now do your AXE notation. So if you haven't already done so, based on the Lewis structures we have drawn, these 4 should be just like the other examples we've done. For these 2, we need to treat each central atom, this carbon and this carbon, and this carbon and this carbon, separate. But at the very least, try and do our AXE notation for these. So if you do that, this would be AX2, this would be AX2E, this one would be AX3, and this one would be AX3E for this one. Okay? Now, for our central atoms over here where we have multiples, we need to figure out this and this separate. So, I can't just cut this molecule in half. I need to look at each attachment. So this carbon right here has 1, 2 atoms attached to this directly, right? This carbon and this hydrogen are attached here. So if there are 2 attached atoms and no lone pairs, that makes this particular carbon AX2. Our other one has 1 hydrogen and 1 carbon. No lone pairs, so this carbon is also AX2. They will not always be the same, but in this case, because they are linear, or because they are symmetric, they will both be linear. Okay, so this whole molecule would be linear, which means our bond angles would all be 180 degrees. If we look at our other one, this and this carbon both have 1, 2, 3, and for this carbon, 1, 2, 3 total attachments. They're all atoms, which means that this would be AX3, making each of those carbons trigonal planar. So keep in mind that this drawing we're seeing here is flat. We're not necessarily representing these in 3D, but those would be our geometries. So linear, and both carbons there are trigonal planar. Now, if we look at our other structures, if we take those AXE notations and convert them to geometries, we see that this one, AX3E, would correspond to a trigonal pyramid, which started with bond angles of 109.5, but now comes down to 107. AX3 would be trigonal planar, and as we just saw a moment ago, that means our bond angles would be 120. And then for our remaining ones, AX2, as we've already seen, would be linear, 180 degrees, and AX2E is one of our bent structures. This is the bent structure with the bond angle of 118. So there we are for all of our molecular geometries there. So I did not write the electron pair geometries. Those are our molecular geometries. All right, now our final examples have to do with expanded octets. The process is exactly the same, but remember that I am not requiring you to memorize the expanded octets, okay? The molecular geometries for expanded octets are in your reference book. You just need to be able to identify what the AXE notation is. Also, just one more reminder, if you're having trouble drawing the Lewis structure, don't forget to pay attention to formal charge to trying to decide the structure, okay? So again, one last time, pause the video and then try to draw Lewis structures for all 3 of the molecules you see here. Here are our Lewis structures. So if we look at all of these, the first and second, you should have exactly the same thing. The reason I have these asterisks on the third one is to point out that if you're basing this on formal charge, this double bond here minimizes formal charge and makes all those molecules have formal charge, all those atoms have formal charges of 0. However, if you drew this as a single bond instead to ultimately make that oxygen have a negative formal charge, I would still have accepted that, but this technically would minimize formal charge the most. Remember, all these fluorines would also still have their lone pairs. The more we do with molecular geometry, the more you'll see these lone pairs left off the outer atoms because it's implied that they're there. But if we do our AXE notation for these, we'd see that this first one would have 2 attached atoms and 3 lone pairs of electrons. The next one has 3 attached atoms and 2 lone pairs. And then our final one has 5 attached atoms and 1 lone pair of electrons. So if we get our electron pair and molecular geometry for all of these based on what we have here, with 5 total attachments, which is this one and this one, our electron pair geometry would be a trigonal bipyramid. Sometimes you'll hear bipyramidal, but it's the same thing. Okay, so that would be for this first one and for the second one. This final one, though, which has 5 plus 1, so 6 total attachments, would mean our electron pair geometry would be an octahedral. Now for our molecular geometry column here, based just off of our AXE notations, that's going to give us our molecular geometry. So our first one would be a linear structure. Again, I told you, you do not have to memorize the bond angles for the expanded ones, but this would be 180. If for our T-shaped molecule, this one has a couple different angles, so we'd really have about 180, and then you'd have less than 90, essentially. And then our final one, AX5E, would be a square pyramid. Okay, and the bond angles for that, if you wanted them, would be less than 90 and 180. Okay? So there we are. I hope that helped with determining the molecular geometry. As you can see, once you have these memorized, or if you're looking in the reference book, as long as you can get the correct Lewis structure, getting to the geometry shouldn't be that difficult, but it does, again, expect that you know the 6 geometries that follow the octet rule. So step 1 is always draw the Lewis structure. Step 2 is get your AXE notation, and that will ultimately lead you to your molecular and electron pair geometry.